Welcome back, everyone. We're going to cover radicals this week, so we're going to talk about main rules of radicals, how to simplify them. Now, simplifying them, which was what we're going to cover in this video, is probably the most important because it's going to be something we'll be talking about all week long. It's relevant to when we add, subtract radicals in the next video, when we multiply and divide them in the video after that, and of course when we solve them as well. So we do need to know how to simplify. It's like working with fractions. We have to know how to use these. We have to know how to work with them and simplify them. Main rule with radicals, though. This is something we're going to remind probably all week. You cannot square root a negative number. Okay, a negative. Let's just big example, -3 or something. Okay, you can't square root any negative numbers. Let's give an example. How about -4 instead? Why can't you square root -4? Well, remember, the whole point of the square root is you have to figure out what two numbers multiply same number. So it's not really two numbers, it's the same number that multiplies equal -4. Let's backtrack to something that you do know how to do. For instance, the square root of 25. Now, you all know the square root of 25 is 5. And the reason it's 5 is because 5 times 5 equals 25. So when I take the square root, I'm looking for the number that multiplied by itself to equal 25. So what number can I multiply by itself to equal -4? You know, what number times itself would equal -4? Well, the thing is, you would probably try -2 and -2. However, -2 times -2 is a +4, not a -4. So those don't work. You could try a +2 and a +2 if you wanted, but again, those are +4, so those don't work. Now, of course, the only way, this is just a law here, the only way you can have two numbers multiply together and equal a negative is if one number is positive and the other is negative. Which of course then means that both numbers are not the same. Because if you have +2 and -2, then it's not the same number. So the whole purpose of squaring something is you're multiplying it by itself. So we can't find a number that multiplies by itself to equal a negative. By definition, those numbers have to be different. One has to be a positive and the other one has to be a negative. So they are not the same. So when I take the square root of a negative number, I get an error in my calculator, and that's simply because there is no such thing. So I'll have to remember that throughout the week as well. Now there is a little bit of a caveat to that. We'll discuss next week when we talk about complex numbers. There's sort of a way around square rooting negatives. But in a practical sense, in a real world sense, taking the square root of negative is not possible. But there is a theoretical way in which we kind of can do it. Alright, so let's use that information. Let's start with our domain. This is before simplifying. So today we're going to do simplifying, but we're also going to do domain. Now domain is x values related, and it's basically what x values can I put into this function? What x values can I use? Sometimes we can use all the x values we want. But in some cases, like here, we're limited to what x values we can use or can't use, because then we have to go back by that rule that we cannot square root a negative number. So what we're going to focus on our domain with this equation y equals 1 plus square root of x minus 4 is we're going to figure out what value of x would make that number a negative value. Because again, we can't take the square root of a negative, so if x minus 4 comes to be a negative, then that won't work. So I have to figure out which values of x I can use, which values of x I can't use in that equation. So all we're really going to need to do, the simple process really is take what's under, I guess put the parentheses in the wrong place, what's under the square root, set greater than or equal to 0. The reason we're going to set it greater than or equal to 0 is because that means it's not negative, right? If it's greater than or equal to 0, it's either 0 or it's positive. So what I'm going to do is take this x minus 4, because that's what's inside the radical, right? Take it and set it greater than or equal to 0. I want this quantity to not be negative. So I'm going to take it, set it equal to 0, and figure out what values of x I can use. So just solving this now, we add 4 to both sides, and we'll have x is greater than or equal to a positive 4. So that means my domain, I can use any x value greater than or equal to 4. That would work. However, what's not in my domain, and you just let's plug a few numbers in just to see how it works, is number 3, right? I can't use 3 because 3 is not greater than or equal to 4. Let's see what happens if I try to use 3 here. I would have 1 plus square root of 3 minus 4. However, 3 minus 4 is negative 1, and at that point we're taking the square root of a negative, which is not possible. So that's why we can't use 3. I can use 4, I can use 5, I can use 6, I can use any number greater than or equal to 4 because that will give me a positive number in there. Anything less than that, though, as you see with 3, I will get a negative result, and I can't take the square root of a negative, so I can't use those values of x. Alright? But the simple rule is just take whatever's under the radical and set it greater than or equal to 0. That's the definition of what we're doing here. That's how we'll solve it as well. So here again, I have 4 and x plus 3 under the radical. So I want to make sure that this quantity is not negative. I want to make sure it's greater than or equal to 0. So we'll go ahead and solve. So I'll distribute first here. 4x plus 12 greater than or equal to 0. I will go ahead and subtract 12. I have 4x greater than or equal to negative 12, and then dividing by 4. I will have x is greater than or equal to negative 3. Alright, so that's my domain. I can use any x values greater than or equal to negative 3. For instance, I can use negative 2, right? Negative 2 is greater than negative 3, so I can plug that in, right? Let's just see what happens when I do that. Negative 2 plus 3. Well, this becomes 4 times 1, right? Because negative 2 plus 3 is 1, and that 4 times 1 is 4. I can take the square root of 4 all day long. But I can't use numbers like negative 4 or negative 5 or anything that's less than negative 3 because those end up being negative there, and I simply can't let that happen. So I can't take the square root of a negative number. Now it's totally okay, x values can be negative as long as the quantity inside the radical is not equated to a negative. So yeah, I can use negative 2 here because that's not the part that matters. The part that matters is the whole thing, right? Negative 2 is fine. X can be negative 2 because it makes what's under the radical still a positive value. So it's okay to use that. All right? It's not the x value that can't be negative. It's just this whole quantity that can be negative. All right, a little bit of a catch as well. We didn't see this in this example, but you may see it in future examples. If you ever divide by a negative number here, then you have to flip your sign around. That's just something we talked about way back in the day. Here I divided by a positive 4, so I didn't have to switch my sign. But if you end up dividing by a negative, then flip your sign around. It always helps as well, by the way, to check your answer, kind of like I just did previously. That way you know you got it right. Because sometimes you might forget to flip the sign. And checking your answer just by plugging in values that should work or shouldn't work can help you figure out whether you were right or wrong. Alright, let's do one more of these. Again, what's underneath the radical is 2x minus 1. I want to make sure that the number is not negative, so I'm going to set it greater than or equal to 0. Of course, solving it, adding 1. I'll have 2x greater than or equal to 1. Dividing by 2, I'll have x greater than or equal to 1/2. And that's fine, it can be a fraction as well, but that's my domain. I can use any x values that are greater than or equal to 1/2. Nothing less, though. Alright, so now let's talk about simplifying fractions. Or not fractions, radicals. First, of course, this first sentence is kind of common sense, but if it's an expression with a radical sign, it's known as a radical expression. Not a very creative term, but of course it is what it is. The one thing you may or may not remember is that what's underneath the radical is known as a radicand. That actually has a fancy name. So the radicand in this one is L squared plus W squared. The radicand in this one is just D, because D is the only thing inside the radical. The radicand here is 2, because that's underneath the radical. 5 is not, so that's not part of the radicand, so to speak, and 4 is not, so it's not either. So whatever's under the radical, we can kind of call it a name. Instead of saying what's under the radical, I can just call it the radicand. That's the only thing we could probably do. Now, here are a couple of rules we need to know to make sure we've simplified our radicals. Alright, so to make sure our radicals are in their simplest form, they have to pass these three things. The radicand, or again, what's underneath the radical, has no perfect square factors, meaning it's not divisible by any perfect squares. Alright. So again, perfect squares are numbers like 4, 1 is a perfect square as well, but we're not going to ignore that. 4, 9, 16, 25, 36, 49, 64, 81, 100. There's more, but we're going to stop there. Again, these are perfect squares because 4 is 2 squared, 9 is 3 squared, right? 16, 4 times 4, 5 times 5, 6 times 6, 7 times 7, so on. So we don't have to check all the numbers, but we want to make sure that whatever's inside the radical is not divisible by any of these. If it is divisible by any of those, we'll have to deal with it. And you'll see that in an example coming up. Number 2, it has no fractions. So make sure there's no fraction inside your radical. Now, it can be a fraction as long as it's not like the previous one I just showed you. This can be a fraction as long as it's not a fraction inside the radical. So if this was square root of d over 4 instead of square root of d over 4, this would work, but this does because it's not a fraction inside the radical. So that's what that means. There are no square roots in any denominator, so make sure that there are no square roots in a denominator. It's okay if it's in the numerator, but not in the denominator. So let's go ahead and move forward. All right, so you can pause these slides if you want to and kind of read them. I'm going to explain them in the examples. So if you're wondering what am I explaining or referencing or kind of going back to, you can look at these. The main thing you really want to realize is these rules here. Square root of a times b, I can separate them out and do square root of a and b separately. And I can do that with fractions as well. Square root of a and b, I can separate them out and do them separately. So that's the main thing you want to realize, recognize, or remember from these slides. All right, so let's try an example. Let's simplify square root of 24. I'm going to write these perfect squares back down just so I have it as a reference. 6, 49, 64, 81, 100. All right, so simplify all these. Now, I don't want decimals. No decimals. Okay. When you simplify radicals, it's not just a decimal answer. I don't need that. Okay, I need to just simplify. It's like simplifying fractions. You don't just make the fraction into a decimal and call it simplified. You simply simplify the fraction. All right, so first thing you'll notice is square root of 24. 24 is not a perfect square, so it's not one of these over here. It's not a perfect square, so I can't just simply take the square root of 24. However, going back to those rules, rule number 1 is it divisible by any other perfect squares. Is it divisible by 4, 9, 16, 25, 36, any of those? Turns out it is. It's divisible by 4, right? 24 is the same as 4 times 6. So what I'm going to do is I'm going to separate 24 into 4 times 6. Technically, it's the same thing, right? 4 times 6 is 24, so I'm still technically taking the square root of 24. But I'm going to separate these out now. I'm going to do square root of 4 separate from the square root of 6. I can break that up. That's a rule that we just showed you here a second ago, is I can separate them individually, and that's what I'm going to do here. And the reason I'm doing that is because I know what the square root of 4 is, right? So let's go ahead and take the square root of 4. The square root of 4 becomes 2, right? That's what that number is. Square root of 4 is 2, so I'm rewriting it as 2. Not the square root of 2, just a plain old 2. Now the square root of 6, that is not a perfect square. What we'll continue is that 6 divisible by any of these perfect squares. Is it divisible by 4? No. Is it divisible by 9? Of course not. It's not. So that is a simplified radical. I can't simplify it anymore. So my answer is going to be 2 square root of 6. All right? So again, figure out what numbers, any perfect squares that are divisible into 24 or whatever your number is. Separate them out. Take the square root of that perfect square, and then leave the other as a remainder, assuming that this cannot be simplified any more than that. All right? So we'll see a couple of other examples. You can start to get the idea. With variables, it's a little different, depending on, I don't know, how your brain works. Some people find these to be a little easier than the numbers, especially if you're one of those who just struggles with your multiplication facts, multiplication table. If you have a hard time with that, then these are probably easier to you. But we'll see. So here are a couple things I'll write down before I simplify this. Now, for even number exponents, all we really need to do is to take the square root. The square root, and this is probably poorly worded, so I apologize, but it gets the point across. The square root is just half. I don't know. I mean, it's just half of it. So an example, what I'm talking about is, if I take the square root of something with an even number exponent, let's say x to the 16th power. The square root of that is just x to the 8th power. It's just really just the exponent cut in half. Because x to the 8th power times x to the 8th power is x to the 16th power. So that's the reason for that. It's really just kind of cutting it in half. Anything like that. So square root of x to the, so now the even number like, say 24, that would be x to the 12th power because it's really just kind of cutting it in half. Alright, so those are pretty easy. The odd number exponents are a little bit trickier, but not too much trickier. For odd number exponents, basically going to apply this even number exponent rule. Take the biggest even number and leave one remaining variable. So that kind of doesn't make sense when I write it down, but it makes sense when I show you an example. Let's take an odd number exponent, for instance, like x to the 7th. X to the 7th, take the biggest even number before 7. The biggest even number before 7 is x to the 6th. So I'm going to write x to the 6th, and then I'm going to have one remaining x. That's my 7th x. That's my odd number x. And I'll just do what I did a second ago with 24, is I'll separate these out. X to the 6th power, and then square root of x. Now, because that's an even number, I can just take it, cut it in half, make that x to the 3rd, and I leave this extra x as a remainder. Alright? So odd number exponents, just take the biggest even number that comes before that odd number, and you can take half of that. And then you have that extra, that odd number x, or whatever the variable is, you have that sort of left over, and it sort of gets left in the radical as a remainder. Alright, so let's look at this one. X to the 3rd and y to the 4th. So first thing I'd like to do is separate them out. Do these separately. X to the 3rd, again, is an odd number, so take the biggest even number, which would be x squared, and then leave one remaining x. Now the square root of x squared, if you know how to do, and then the square root of this x, that'll be my remainder. So the square root of x squared is just a plain old x. The square root of x is, I can't really do anything with it. It's remaining as a leftover. Now I can focus on my y to the 4th. Square root of y to the 4th, because it's an even number, all I got to do is cut it in half. So that's going to be y squared. It's going to be the same thing. Just bring it down. So here's my answer. Typically, though, we like to write the answer a little bit neater. So anything that's not inside the radical, I'm going to write in front, and then whatever's in the radical, I'll write last. So I'll write this x, y squared, and then square root of x. So these two things are not inside the radical, so I put them up front. I usually write the radical thing last. All right? So this one is kind of a combo of the two. I just do them separately. Square root of 48, square root of a squared, square root of b. And work them out. So again, it's kind of like GCF in a way. Those numbers. We want to figure out what perfect squares I can divide 48 by. But at the same time, I want to choose the biggest perfect square, because otherwise I have to do this problem a little more. simplify it even further. So you might be thinking 4 and 12, square root of 4 and times 12. 4 times 12 is 48. However, the only problem with that is you'll be able to take the square root of 4, but the square root of 12, this is still simplifiable. It's not fully simplified because you can do 4 times 3. Because 12 has another perfect square factor. So we'll have to repeat that process or just do it more than once. So, if you haven't caught on already, the biggest perfect square I can divide 48 is 16. So let's do that. 16 times 3 is 48. So I'll do these separately. I'll have the square root of 16 and then the square root of 3. Of course, I know the square root of 16 is 4. And the square root of 3 is my remainder, so what's left over. Alright, so again, find the two numbers, multiply 48, figure out which of these perfect squares is divisible into 48, and then take that square root out. Now, the variable is a little easier. Square root of a squared, because it's an even number, we'll just take it in half. That's just going to be a regular a, right? I'll bring that down. And the square root of b, it's an odd number exponent, but it's just b to the first power. I can't really do anything about it, so it's just going to be left the way it is, and this is going to be my answer. But again, if it's not inside the radical, I'm going to write that out front. If it is inside the radical, we usually write that last. So this is going to be 4a square root 3b. If you're wondering why I wrote the 3 and b together, it's because it's basically like this. Even if square root of 3 and square root of b are separate, putting them together is the same thing. So square root of 3 and square root of b is just square root of 3 times b. Alright, of course 4 times a, that's not inside the radical, so I figure that on the outside. Alright. This works with fractions as well. First thing you want to do is see if you can simplify the fraction. If you can't, then just go ahead and start separating it out. So square root of 5 and square root of 4, I'll do these individually rather than trying to do it at the same time. So square root of 5, again, is square root of 5 is 5 is by any perfect squares. No, it's not. I can't simplify that down anymore. So it's going to be the way it is. Square root of 4, though, I can simplify. I know that's 2. So my answer is square root of 5 over 2. If it meets all the criteria, there's no perfect square inside the square root. There's no fraction inside the square root. And I don't have a square root in the denominator. Remember, there's 3 rules we wrote at the beginning of this. Now, b, again, main thing you probably want to do for fractions is simplify first. The main reason for this is it just less complicates the problem, makes things a little easier for you. So before I separate these out like I did with this problem, I'll just simplify m to the third over 9m. Because there's 3 m's on the top and there's 1 m on the bottom, this m will cancel with one of these m's, making that m squared. So this should be m squared over 9. Again, if you're wondering why or how I did that, remember this is pretty much the same as m times m over 9 times m, right? This is m to the third minus 9m. Well, this m cancels with that one, leaving you just with these 2 m's and a 9 m squared over 9. And now I'll separate these out. It makes this problem a little bit simpler. I have square root of m squared, this square root of 9, making this m over 3. Alright, I'm going to kind of cut it off there. We've covered a lot of examples. I usually only do like one of each, but I figured all these were so different. I wanted to make sure you sort of had a full, thorough look at all different types of problems you might have to simplify. Because this is going to be one of the main things that we'll be using all week is simplifying these fractions. Or not these radicals, okay? Simplifying these square roots. Super important. Hope it helps. Come back to this if you need to. I will see you guys in the next video. Bye-bye.